think somebody should start the recording. Thank you very much. So good morning, and uh, today we'll continue our discussion on dimensional reduction. I will discuss only one more method in this particular under this particular topic, and that is a very effective method and proposed quite a bit early by uh, Professor Ronald Fisher, who is a pioneer in statistics and in areas, probabilities and others. So in this method, we'll see that how this kind of dimension, how we can reduce the dimension. In fact, we are reducing to only one dimension itself in this method, so that you can effectively classify the samples. So we will be talking about two-class classification problem here, and in like finding out principal components. That means a direction where you are maximizing the variances of the projected data points. In this case, just a minute, I will take just 1 minute break. Okay. Sorry for the interruption. So we are discussing about this particular method of linear discriminant analysis, where we'll see that we will be again projecting the data points on a particular along a particular direction, on an axis along a particular direction. But the objective is a bit different here. The objective is to maximize the performance of a classifier. Instead of having the reduction, instead of keeping the information content intact, preserving the information content as much as possible in the reduced dimensional space. Somebody's microphone is no. Yeah, please. Please unmute your microphone. So as I was mentioning, in PCA, we are finding out the directions, first principal component, if I consider, where the maximum variance of the projected data points could be achieved. But when we consider a classification problem, there is a level data sets. Now, in this case, that direction may not be efficient for discriminating two classes, because you see that projected data points may overlap in that direction. So just let me give you one figurative example. Consider these two classes, which are shown by different colors and shapes of the data points. And you have seen a dotted line as an axis along which on which you will be projecting them. So you see that in this case, the projected data points are overlapping, but there exists a direction, and we may consider that is also direction of the principal component, because that is the say variance. The variance is maximum in that direction. But no, if I consider another direction, say this direction with respect to this data point, a kind of horizontal axis. So here we can see that projected data points are clearly separated into two regions. So they are very much separable, and So in that case, the classification task is easier. And not only that, your data points are projected onto only onto one-dimensional space only. So from that point of view also, your classification becomes very simple. It's kind of finding out the intervals. It's a kind of interval classification problem, if you can say. So well separated, but not along the direction of principal component. So these are just a figurative example. And in our today's topic, we'll be discussing how to find out this direction, which will maximize the separation of these projected data points. So, and this classifier or this direction on this method, and also I should say that given the directions, you get this method of getting projections, and then you can always determine certain threshold gap between these two intervals. So, so we call this kind of classification as Fisher's linear discriminant classifier. So, this is mathematically. Let us formulate this problem. Say you have a data points in the d-dimensional space, and suppose since you have a labeled data set, that means there are two classes. I considered there are two classes. I'll be discussing with respect to two-class classification problem. Its multidimensional extension is non-trivial, but similar. So we'll be restricting ourselves to two-class problem only. So you have these n1 points in, say, class W1, and there are, say, n2 points in class W2. So, and we consider the total data points is n1 plus n2 equal n. So this is how your data set is given. Now, you may consider a line with a direction u, right, in that space, in the multidimensional space. So projection of data on u is this. You may consider u is the unit. U is the unit directional vector, unit vector. So projected data point is this. Otherwise, no, you have to normalize the direction. So let us consider it's an unit vector. So you get an one-dimensional subspace representing the data. That is the first thing. And then we will consider that how to define an objective functions of discriminations of two projected sets. That means the separability. So we will be considering the mean and spread of the distribution to consider the interval along on which the data set is lying. So there may be outliers also. So instead of taking the range of projected data set, interval of the projected data set, we will be considering simply mean, and around mean, consider there is a standard deviation. So around mean, that defines the interval, mu plus minus sigma. So that may be that is the definition of interval in our case, statistical definition of interval. So that's why we will be now discussing how actually you can compute these two quantities in the projected space directly from the data point and given a direction, right? So in the data set itself, you can compute the mean of the data points in class W1 and mean of the data points in class W2. So class 1 and class 2. So this is directly computable from the data point itself. So the projection of means, since it's linear operation, computation of mean is a linear operation. So projection also would be would preserve the linearity, which means that if I project the means itself on that axis, that will be also mean of the projected data points of class W1 and correspondingly other. That means you have to project the means only. So that's what you do. Huh? So you get M1 transpose U. So U is the unit vector, please note that, and M2 transpose U, right? So these are it can be very easily proved. You can check it out. Now, a measure of separation is that once again, when we are considering the data sets measure of separation, data sets variability first. So measure of separation is basically there, as I mentioned, that we will be considering an interval. So interval is defined as in the projected space, mean and plus minus, say, standard deviation. So we need to compute the variances of the projected point, and from there you can get standard deviations. So that means in the data point what is given to you, you can compute the covariance matrix. And if you remember our previous lecture, if I give you a direction unit vector, so in that, along that directions, you can always measure the variance by variance of the projected point by simple linear operations. So measure of separability here, we are considering the difference. So that is the measure of separation. Of course, we'll see that it needs to be qualified by the variances. So that's what does not consider the variance of data. So we normalize this separation by a factor proportional to class variances. So the scatter of data belonging to class C, actually instead of variance, we'll be using scatter, which means that it is sum of squares of deviations. So we define the scatter of data belonging to class C in the projected space. This is the scatter of data for class C. It's in the projected space. Please note that it's not scattered. Scatter is a scalar quantity here, which is basically the variance, measure of variance multiplied by the number of data points, number of samples, right? So that's what. Where and the measure of separation is defined as the normalized, so this is the objective function. So that is what you just know. To make it unitless, you simply square the distance d between two means, and then you divide it by s1 square, s2 square. So your objective is to, we'll see that how this scatter can be computed from the covariance matrix later on. So the objective is that we need to obtain the corresponding direction. Once again, it's an unit vector in that space, maximizing this particular measure of separation, normalized measure of separation. So that is your objective here. So this is the mathematical problem. Any question do you have in this figure? Okay. So let us proceed further. You see that scatter of projected sample should be small, because in that case you are, which means the standard deviations are small, so you get more reliable, level. But it depends upon the class variance. It may not be always small. So, but that is the measure we are using. Now we consider that how you can measure, how you can define the scatter or obtain the scatter from the data point directly. That means with respect to data point, and if I give you the directions, I should be able to compute the scatter like I have computed the means. So once again, the scatter matrix for sample of class C in original space is defined in this way. You see that this is the covariance matrix of class C multiplied by number of samples. That's all. So that is what is the class scatter matrix. SC is a scatter matrix, as you can see here. And similarly, within class, so we define within class scatter matrix. That means SW is S1 plus S2. That means each class has its own scatter matrix, and if you add them, that is within class scatter matrix. And whereas as we have already defined the scatter, a scalar quantity which is not a matrix, on the projected space, now you can see that this is the definition of the scatter, and you go ahead with the computation. Actually, this is the proof of the previous result what I showed, that given a covariance matrix, given a directions, how can compute the variance of the projected data points along that directions, it's the same. Only though you see that normalizing, that is the number of samples are not taken into considerations in the formulation. So you can write in this form each data point. You can see y, which is the projected data point. So which means I can write it in this form. I can write it as x transpose u or u transpose x. It doesn't matter. Similarly, my1 is the mean of the class w1. So that is also written in this form. So I hope now it is clear. Huh? And you know that this quantity can be written in this form, right? So that is how you are writing it. Actually, it's a square. So if I use the column vector representation, this transpose should be in a different order. So anyway, so you bear with this convention. In this case, it is considered as a row vector representation, but usually have taken column vectors, so it should have been reversed. So dimensionality, now you have to always check. So you can bring out u transpose u out of them in this fashion with the linearity operations. And finally, you can write it in this form, which is once again the corresponding, covariance matrix, which is corresponding scatter matrix of the data point. So you can write it in this form. That row vector and column vector representation is somehow at this point bugging me. I will check it also later. But this is the way you can check this. No, you can compute the scatter matrix. Given the scatter matrix, you can compute the scatters. So you can see here. See, this is a scatter matrix for class 1, and that is, as I mentioned, that is nothing but the covariance matrix multiplied the number of samples for the class 1. And you can compute S1 square. Similarly, you can compute S2 square, and since you are adding them, so effectively from this definition you can write here S1, S2 within class scatter matrix. So from there you can replace the you can replace the corresponding SW, and another quantity is the between class scatter matrix, which is basically the M1 minus M2 into M1 minus M2 into transpose. So it's a column vector representation. So means of W1 and W2. So from there you can show that this is the between class scatter matrix. I mean, between class scatter matrix you are using simply the the difference of mean as the, here it is column vector representation. Oh, sorry. This is a scalar quantity, my1, and my1 is a scalar quantity. That's why no, I'm sorry, I understand that. I'm getting confused. Let me also tell you. See, this you can also write this. I mean, you can exchange this. two expressions, because this is a scalar quantity. This quantity is a scalar quantity. So whether you write transpose or not, it doesn't matter. So for the convenience, I am using this representation because then I can bring it into this form, into this definition. That is true for also the previous case also. So this was a scalar quantity. So whether I put transpose here like this or the way it has been given, sorry, then it doesn't matter, right? So if I put in this formulation, then only you can write it in this. So here I am always consistently following column vector representation. I hope you have understood where is the confusion and how it got clear. So we can rewrite the optimization functions like this. Like this was your objective function, as I mentioned, that square of the separation of mean divided by their sum of scatters, the square of sum of square of scatters. That is a normalized way of measure of separation, and that can be expressed in the form of the direction and also the measures from directly from the data point in this function. So you are trying to maximize this, and the constraint is that u should be a normalized vector. U should be a normal vector, unit vector. Sorry, unit vector. Now it can be shown that this is achieved when U is the solution of this. No, it's a generalized eigenvalue problem. So U is the solution of this, and which means that SW inverse should be invertible. And as I mentioned that now SW inverse SB gives you the corresponding eigenvalue. So one of the things is that for any vector, say SBZ, SB is a between class scatter matrix, if you remember. Now, since if I go to the between class scatter matrix definition, now this is the between class scatter matrix definition. Now you can see that this can be represented as k into m1 minus m2. Note that m1 minus m2 is a vector. So SBZ can be always represented in this form because I can write it in this way. So this is the between class scatter matrix definition, m1 minus m2 and m1 minus m2 transpose z. Now this part is scalar because this is a dot product of this vector, right? This is the row representation, this is the column representation. So this is a scalar quantity. So you get k, you can bring it before m1 minus m2. So we can write in this way. So the point is that SBU can be now represented as k into m1 minus m2 itself. So which shows that your right. So your solution is something like this. So Q is SW inverse m1 minus m2. So that would be your solution because you have already represented in this form. So here only, of course, direction matters. So that's why you are not considering the value of k. And so finally, this is your solution. And the constraint here is that, of course, your within class scatter matrix should be invertible. That is the constraint. So this is the way you can get a direction where you can maximize the separation with respect to the separation measure what I discussed, normalized separation measure between two classes. That is the directions. So any question? So now you understand that what is this method now. So once you derive U, the task will be that you project the data points and then you define the corresponding find out that. So ideally, I mean, if they are non-separable, then you can have a very definite answer. Otherwise, no. If they are overlapping, definitely there would be a fuzzy boundary between them. So you have to consider the corresponding range where you can definitely say the samples which are belonging to certain classes and where there are fuzziness, etc. You can take various ways of this decision, but from the dimensional reduction point of view, you are reducing the data point to one dimension by maximizing the separation of the projected data points between these two classes. So one example, computational example that I'll be considering. So as you see that computation wise, you have to compute these factors for finding out the solutions here. You have to compute the inverse of the within class scatter matrix, which means once again covariances of, or I should say covariance into number of samples. So you have to compute that sum of, I should say that is scatter matrix. So let us say scatter matrix of the class 1 and then scatter matrix of the class 2, then add them. That would give you the within class scatter matrix. And then the inverse has to be computed. And the other one is that you have to compute the mean, then take the difference, and this is how you will get Q. So with examples, let us consider one numerical example. Say we have taken these three, I think I have taken the same data set. If you remember that if I add them, x plus y plus z equal to 10, right? That was the plane on which these data points are lying, and there exist, I mean, it is possible to represent just by two directions in the space because they are lying on the plane. But no, I am also providing you the class levels. So some of them I am putting it in class 1 and the other in class 2. Then we would like to see that what is the directions where you get this maximum separability. So you have to perform the linear discriminant analysis to get the optimum. Then also we can perform the PCA on the whole data set and check the service. So PCA we have already seen. If I have added another point, then it will be a little bit different. So once again, you are defining the data matrix for class 1, like all column vectors are a single data point, and whose since I'll be computing the scatter matrix. So the mean is replicated in 3 columns because you have to subtract, and then from the definitions you do this. So this is the definition of the scatter matrix. So you get S1. Similarly, the other scatter matrix S2, and if I sum them, you will get within class scatter matrix, and then you have to invert it. So this is within class scatter matrix. This is the within class scatter matrix, and what you need to do, somehow subscripts are missing, so W should be a subscript here as per my notation. So you have to compute the inverse of scatter matrix into mean 1 minus mean 2. Mean 1 is mu1 and mean 2 is mu2 here. I mean, mu1, mu2 is shown as a matrix, so one of the column of these matrices. So from there, you get these particular directions, and then you should take the normalized direction. So separability, since it is separability, and it will be, if you don't normalize, it will be basically scaled up. So normalizations may not be required in practical cases, but of course, for data, if you are going to use the data values, normalization should be there. Otherwise, no, your objective is classification. So you can go ahead with these values itself. So you see that y1 and y2 in this direction, along this direction u, y1 lies between 19.31 to 22.2, and y2 lies between 5.43 to 9.55. So which means there are two distinct intervals on which these data points are lying, and it's a good, you can separate it, but these are well separated. You can just observe from this particular result. Now, if I consider PCA, once again, as you know that in PCA you have to compute the covariance matrix, then you should get the eigenvalue. So there is an additional data point, so that's why it is not exactly the same result. You get also a third eigenvector, which was earlier, it was, there was a third eigenvector, but third eigenvalue, non-zero eigenvalue. So earlier it was 0, but now it is 1.47. So some variance is there along with 3 also. So in the PCA, you get, suppose I am using this one of these direction, principal components directions, and I'm taking the projected data points in that directions. So you can see that this 13.98, there is a it's separated, still it is because the range is 14.05 to 16.18 for Z2 and 13.9 minus 1.65 to 13.98 for Z1. So still there is a little gap between them in the interval, but the separation is much less. So it has reduces margin of separation to a great extent. So this is just one example that how LDA is more useful with respect to the classification task than the PCS. So just to summarize whatever we have discussed today, or under this topic also we discussed in the previous class, that we particularly considered three methods here. One is feature selection approach, that is subset selection approach, and their forward and backward sequential selection methods we discussed. Then unsupervised dimension reduction method, PCA, is one such example. And then supervised dimension reduction method, because you have the class levels, then LDA is another such example. I think this is all. So with this, let me stop today here because this is the end of this particular topic, and then again we'll meet after your puja break, and we'll start with a new topic on linear discriminant analysis. So if you have any questions, let me know.
Sir, hello.
Yeah, tell me.
Sir, when will our next classes will held?
So what is your understanding?
No, sir, I want to know when will our next classes will held.
So that's what I'm trying to understand. What is your understanding? Have you checked our academic calendar?
No, sir.
Please check. In our website, there is an academic calendar. After the puja break, the first class, first Wednesday, whatever you get, I mean, whenever the working days, first working day, the class will be held. Please check the calendar. And so this kind of questions should not be asked.
Okay, sir.
Unless the regular schedule is for some reason we are not following, because I will not be able to take class, then I will announce. Otherwise, every regular class will be held. Any question? Okay, so I see there is no question. In fact, I thought that after the quiz, we will have a lot of questions and we have some time to discuss. Okay, bye. See you after the puja break. Happy puja for all of you.
Okay, sir.